Let me show you why. Let's start off with an element that's also important to us, but slightly different. And that's nitrogen. Now, how many valence electrons does nitrogen have? 5. Okay. And if I were to draw kind of a Lewis representation, I'd get something like this. If I were to draw out the outer shell, which is the 2s, 2p shell, I would see that, let's see here, we got 2p. I would see that the first 2 electrons went right here, and I would see that the last 3 electrons would go into the 2p orbital. Now, just venture a guess. How many bonds do you think nitrogen would like to form? I got 3 from some of you. What do you think? How do you decide 3? You can't answer because you've still got Skittles in your mouth. How about somebody else? Okay, we're missing 3 electrons from achieving our octet. Okay, and it turns out that we also fortuitously have 3 unpaired electrons. So wouldn't it be nice if we could have something come in with its 3 electrons to bind to the nitrogen? So let's look at one of the common forms of nitrogen, which is ammonia. Okay, looking at ammonia here, we can see that it is bound to 3 hydrogens, and it has a lone pair of electrons that's not involved in any bonding. Because nitrogen is bound to 3 different groups, they don't have to be different identities, but 3 separate atoms, we say that nitrogen in this case is trivalent. Okay. That's not to say that those lone pair of electrons are non-reactive, because if I were to react this with acid, what I would find is that I could produce the ammonium ion. So this is ammonia, and this is ammonium. Now, does anybody want to take a stab at what the valency of ammonium is? How many things are bound to it? 4. Okay. When it was only bound to 3 things, it was trivalent. And when it was bound to 4 things, it becomes not quad. Guys, you have to pick either Latin system or Greek system and stick with it. So if we start with trivalent, we go to tetravalent. All right, so valency is a reference to the number of bonds that a particular element is making. Okay, let's look at something else that we're familiar with. Let's look at oxygen. How many valence electrons does oxygen have? 6. Okay. And if I were to look at the electronic configuration, let's see here. One, 2, 3, 4, 5, 6. Okay. Based on that, what do you think the typical valency of oxygen is going to be without being charged? 2. Okay, oxygen is going to be divalent. So a great example of that is our friend water. Okay, so this is another handy application of these Lewis structures and recognizing the electrons in the outer shell. We can predict how many bonds that a given element should form to its partners. But now let's take a look at carbon. Okay, carbon here, how many outer shell electrons? 4. Okay, and if I fill these up, one, 2, 3, 4. Now, based upon what you see up here, based upon the examples that I gave with oxygen and nitrogen, what would you expect the valency of carbon to be? Why?
Because there's 4 electrons.
Okay, there's 4 pairs of, or sorry, there are 4 electrons that are missing. But how many unpaired? 2. Okay, so if I look back at the example of oxygen, you'll notice that I had these guys that were paired that contributed to being the lone pairs. If you go up to nitrogen, this pair contributed to being, again, the lone pair. But you bring up an interesting contradiction. Okay, based upon the number of unpaired electrons, the way this is drawn, I would expect carbon to look more like this. I would expect it to have a lone pair of electrons and to be divalent. That's what I would expect it to do. But of course, that's not what it does. It's missing electrons, right? It's unhappy. This is called methylene. By the way, this is an actual chemical entity. It does exist. You can't put it in a bottle. It doesn't last that long. But it was actually discovered by Donald Duck. That got somebody's attention there. There was an old comic book, I believe back in the 1940s, where Donald Duck talks about mixing methylene with oxygen to make speckled nitrogen that became duckamite or something like that. But it was kind of funny because at that point we weren't really sure what methylene was. By the way, that comic book has been not quoted, I should say, it has been cited in academic journals. As a matter of fact, a lot of people don't know this, the guy who did the comic work for Donald Duck was so good at coming up with these very realistic sounding scientific terminologies that one of his comic strips served as a way of keeping a chemist from getting a patent on a process, because this guy had actually come up with the process just as gibberish. And this guy made it work, and it turns out the patent goes to the artist, the guy who came up with the idea first. So that's a little piece of Americana for you. All right, so clearly there's something weird here. Divalent carbon doesn't seem right. But the problem is how on earth do I get this to translate anyway else? The answer to that is called hybridization. Okay, and hybridization, okay, is the mixing of orbitals. Okay, so in the case of carbon, like we said, we had 4 electrons being spread out between the 2s and the 2p orbitals. And what carbon's able to do that other elements don't do quite as well is to take those orbitals and combine them together. Not only combining them together, but redistributing the electrons. So instead of having a pair of electrons here with two unpaired electrons, okay, what we wind up with is a system of 4 orbitals. And I haven't broken any physical laws here because I started off with 1, 2, 3, 4 orbitals, and I'm winding up with 4 orbitals, except these orbitals each contain 1 electron. Okay. Now, what do we call these things? They're not s orbitals, they're not p orbitals, they're not really sp orbitals. They're 1 part s and 3 parts p, right? Because we have 1 s orbital here and 3 of the p's. So we call this sp3 hybridized orbitals. Now, there are other types of hybridization that carbon can take on that add to its versatility, but we're not going to talk about those just yet. Okay, let's talk about the implications of this. Okay, instead of having an s orbital, which is, let's see here, spherical, or 3 p orbitals. I want to draw them all on the same plane here just to save ourselves from having to deal with all the different axes. Okay, and also to keep things clear, I'll put the nucleus in here. If this is a true hybrid, a true cross between the s orbitals and the p orbitals, we would expect the resulting orbital to have properties that are akin to both of them. But which one should it look more like? An s orbital or a p orbital? The p, right? Because the p is making more contribution to it. So what we do here, to show them coming together, and this is going to be comes kind of an exclamation point type of a shape. But remember, I have to make the same number of orbitals that I started with. And the shape that I've arrived at here is derived from a linear combination of the s and p orbitals. Are there any questions about that? Now, when I drew the p orbitals all in the same plane, all oriented in the same direction, we know that the x, y, and z axes are used in the actual molecule, right? In other words, we know that we have our nucleus, and we have one p orbital that's kind of going towards us, and one that's going left and right, and one that's going up and down. Why do you think the p orbitals orient themselves in that manner? What lives in the orbital? electrons. And do electrons like to be next to electrons? No. So what happens when you orient those orbitals orthogonally to one another? You're actually you minimize the contact. Well, there's no contact between the electrons, but you're minimizing the chance of that happening, right? Okay. You are making sure that those orbitals are as far away from one another as they can possibly be. And this is what was the question that came up last class. How do we know that water's going to be bent? The reason we know that water's going to be bent because we know that the electrons want to orient themselves in a way that they are as far away from each other as possible. Okay. Now, if we look at the sp3 orbital, do you think that it's going to align itself the same way as the p orbitals do to make sure it optimizes the distance between them? No, they're not going to, because its shape is different. You'll notice you have a large lobe and a smaller lobe, okay? And that asymmetry leads to something very interesting. Let's see if I can convince this. There we go. You see, carbon, because of its sp3 hybridization, okay, because it has 4 orbitals with 1 electron each, what is the implied valency of carbon? Is it divalent still? What do we expect it to be? Tetravalent. Okay, we expect there to be 4 bonds. And if we take carbon and we make 4 bonds to hydrogen, we make a very simple molecule called methane. But I want you to take a look at this because this is pretty slick. By the way, you have access to this software as well. This is called chemmagic.com, CHEMAGIC. I used to recommend everybody go out and buy a $50 set of model kits, but there's no reason for it now that we have this. You can actually manipulate the molecule. And what you'll see here is that the molecule has a 3-dimensionality to it. Okay, and it's also got a ton of symmetry to it. But the way that these carbon-hydrogen bonds are oriented relative to one another, we are minimizing the interaction between the electrons. So in other words, the electrons in this carbon-hydrogen bond are as far away from the electrons in this carbon-hydrogen bond as is possible. Okay, so let's start seeing it.